Good evening. My name is Shrikant Srinivasan. I'm going to be talking about ellipsometry. My registration number is 16 BME1113. So, what is ellipsometry? Ellipsometry is a non-destructive light optical analysis technique that requires neither sample preparation nor special measurement environment. As we know, many of the characteristic techniques that we use to characterize materials, they require the sample to be in a particular shape or a state or condition. But unlike them, ellipsometry does not require any special sample preparation. Samples of almost any size and shape can be examined as is and are unaffected by the process. So, some processes they involve destruction of the sample. For example, TEM involves destroying a part of the sample is destroyed. But ellipsometry is not like that. It's a non-destructive technique. The non-contact nature of the technique lends itself to measuring materials like semiconductor wafers, optical components like mirrors, coatings, and LCD displays. Ellipsometry uses the fact that light undergoes some change in polarization when it is reflected off the surface of a material. Light, when it falls on a material, it is not reflected back in the same phase. For example, if a light is incident at 90 degrees polarization, after reflection, it undergoes some change in polarization, and this change in polarization is detected by ellipsometry and material is characterized. Although most commercial ellipsometers are designed for operation only in reflection geometry, JASCO instruments can also be configured for transmission work. So any transparent material can be studied, and in this case, for example, the bulk material's properties can be analyzed. In the case of a LCD display, both the reflective surface layer and transmission information are required. With a semiconductor wafer, only reflection data is required and no simpler instruments can be used. Ellipsometry does not directly measure thickness or optical constants. It measures change in light polarization expressed as psi and delta. So basically, psi and delta determine the differential changes in amplitude and phase respectively, experienced upon reflection by the components of the electric vector parallel and perpendicular to the plane of incidence. In the ellipsometry, it is usual to describe the polarization states in a system of two orthogonal basis vectors. The S direction stands thereby perpendicularly to the plane of incidence. As we can see from this image, the S direction stands perpendicular to the plane of incidence. The measured variables are the two ellipsometric angles. So this angle is delta and this angle is psi, whereby delta is the phase difference between P and S, and psi is a measure for the change of the absolute value of Rs and Rp. Because the ellipsometry measures the ratio of these two values, it is a very exact and reproducible measuring method. So, what does ellipsometry tell us about the samples? Variable angle spectroscopic ellipsometry tells us material optical constant Nk directly, how these constants vary with wavelength, variation with incidence angle. By computer modeling, thickness of single or multiple layers. By processing the data from many points on the sample, generate 2D or 3D maps of the sample surface. Ellipsometry is very sensitive to ultra thin films of 1 angstrom up to about 1 micrometer. For multiple layers, the materials must be transparent or semi-transparent. By reflecting a light beam of the surface of a sample, the polarization of the beam is altered. In the simplest ellipsometer, we illuminate the sample with linearly polarized light beam, and after reflection, the beam is circularly or elliptically polarized to some degree. We use a polarization sensitive analyzer to measure the degree of elliptical polarization. By doing this, we obtain the refractive index N and extinction coefficient K of the sample surface. Refractive index N. Propagation speed of the wave through the sample and direction of propagation. Extinction coefficient relates how much energy of the wave is absorbed in a material. Both vary with wavelength and temperature. Thickness. However, ellipsometry can also provide more detailed information. For example, many new materials, including semiconductor wafers, are made with single or multiple thin layers of different materials, deposited or grown on a substrate layer. 3 examples of this are SiO2 on Si, SiO2 on glass, and indium tin oxide on glass. In this case, we already know the refractive index of the materials from reference work, but we want to know the thickness of the layers. Even a few angstrom thin films can be measured extremely accurately. Thank you.